Scholars, Miss Gardner here to take you through our last lesson on acids and bases before we go into a new unit. So today will be review and wrap up, and then you'll finish off today with a quiz. All right, so to review, I'm going to go over a few topics that Miss Fecht talked about in her videos and some that you saw in my lab video. So what is an acid or a base? Well, that was kind of an elusive definition for a while. So Arrhenius came along and gave us our first definition. So many scientists tried to come up with a simple definition for many years, but they couldn't find one that actually applied to all known acids or bases. But Arrhenius in the late 1800s was the first to define acids as something that released H plus ions when they're dissolved in water. So what does this actually look like? Well, you have a beaker of water here. Say we add HCl, or hydrochloric acid, to it. When it dissolves in water, it separates into its ions, H plus and Cl minus. And since it releases H plus ions, that makes it an Arrhenius acid. An Arrhenius base is something that releases OH minus ions when dissolved in water, or hydroxide ions. So if we add sodium hydroxide to a beaker of water, and it dissolves, it will separate into Na plus and OH minus. So that releases hydroxide ions, and that is an Arrhenius base. So we also heard the term Bronsted-Lowry definitions. So Arrhenius' definition was a pretty good way to classify acids and bases, but it wasn't perfect. For instance, a really common base, ammonia, didn't fit this definition. It didn't contain hydroxide. So how could we make that a base if it doesn't follow that definition? And then just a side note, ammonia is a key ingredient in Windex. All right, so in the 1920s, Johannes Bronsted and Thomas Lowry came up with similar definitions for acids and bases, and they actually worked separately. They didn't work together. But since they discovered or came up with this at the same time, we're going to refer to these as Bronsted-Lowry acids and bases. So a Bronsted-Lowry acid is a proton donor, so something that gives away an H plus ion. A Bronsted-Lowry base is a proton acceptor, or something that receives a proton or H plus ion. So if we want to consider our same reaction before, so say we take HCl, hydrochloric acid, and we mix it with water, our HCl, acting as an acid, will donate its proton to water. And then our final products will be Cl minus, chloride ion, and H3O plus. This is called the hydronium ion. This is a particular ion that has a special name that we use a lot, hydronium. All right, so that is how our Bronsted-Lowry acids and bases work. So if we just looked at a chemical formula, could we tell if it's an acid or a base? Well, sometimes yes. Sometimes we might need to know more. We might need to see the structure. But there are some simple identifiers that we can use. So for acids, a lot of acids actually fit both Arrhenius and Bronsted-Lowry definitions. So let's look at a couple. So here we have HCl, or hydrochloric acid. We have H2SO3, or sulfurous acid. H3PO4, phosphoric acid. H3BO3, or boric acid. And HF, hydrofluoric acid. So what do you notice that those all have in common? All right, well, those all start with an H, or a proton. All right, so those ones are all acids. So we're going to use that as a way to identify them. H starts with an H, it's an acid. Now let's look at bases. Bases are not quite as consistent. Some of them fit the Arrhenius definition, and some better fit Bronsted-Lowry definitions, but we'll simplify it for what we're going to do here. All right, so let's look at some bases. NaOH, sodium hydroxide. LiOH, lithium hydroxide. We have magnesium hydroxide, potassium hydroxide, and then we also have ammonia. All right, so if we excluded ammonia from this, what do all of those have in common? Well, they all contain a hydroxide group, or that OH group. All right, so we're going to use that as a simple way to classify something as an acid or a base. So if it starts with an H, it's an acid. If it ends with an OH, it's a base. Now make sure when you're looking for a base, you're not just looking for an O and an H anywhere. It needs to be together as a hydroxide ion. Okay, let's do some practice problems. So here we have HC2H3O2. Is this an acid or a base? Well, I hope you saw that it started with an H, so it's an acid. All right, H3O plus, this is our hydronium ion. That also starts with an H, so that's an acid. All right, let's look at this next one. This is a more complicated compound, so NCH3,4OH. Well, I see that contains an OH, so that's going to be a base. All right, HNO3. So this contains H and O, but is it a base? No, they're not together. It starts with an H, so it's an acid. BaOH2, I see that OH group, it's a base, and then OH minus, it's going to be a base. All right, so that's going to be our simple way to classify if something is an acid or a base. All right, so we can also consider the strength of an acid or a base. So you may have heard of something being referred to as a strong acid or a weak base. Baking soda, for instance, is a weak base. Well, let's look at an example. So why does HCl have a pH around 2 and vinegar has a pH around 3? They're both acids. Why do they have different pHs? Well, that has to do with how well they release H plus ions in water. So if a molecule completely dissociates in water, or it completely separates into its ion components, that's going to be a strong acid. A weak acid only partially dissociates. So if I dissolve something in water and some of it stayed together in a compound, but some of it split apart into its ions, that's going to be a weak acid. The same can be said for bases. A strong base completely dissociates in water. So like we saw in the previous slides, when we put sodium hydroxide in water, it completely split apart. The sodium was separate from the hydroxide. So that would be a strong base. A weak base only partially dissociates. So some of the molecules will be separated, some of them will still be together. All right, so strong acid and weak acid, or strong base and weak bases, basically how well do they release their ions in water. All right, and finally, what happens when we actually mix acids and bases together? Well, when we have an acid-base reaction and they mix in solution, they act to neutralize each other, or basically cancel out each other's acid or base properties. So if I have something that's really acidic with a pH close to 2 and something that's really basic with a pH close to 12, if I mix those together, the final solution's pH is going to be closer to 7 because that's closer to neutral. So a typical reaction will look like this. Acid plus base goes to salt plus water. If we fill that in with some examples, here's HCl plus NaOH. Notice I've color-coded here so you can see how my proton is moving between them. So here, this proton is donated to OH. OH accepts the proton, so this will be my base. This will be my acid, and then my final product will be sodium chloride and water. So salt plus H2O. And so here, salt doesn't just mean NaCl. Salt actually means any kind of simple ionic salt, so a positive ion and a negative ion. So looking at this reaction, do you remember what type of reaction this is when two ions are swapping places? Well, this is a double replacement reaction. So acid-base reactions are typically double replacement reactions. We're swapping ions between our two species, and one of the ions that's going to be moving is our H plus, or proton. All right, so let's look at a few examples, and this is where we're going to wrap up today. So here I'm going to show you some acid-base reactions, and I want you to circle the Bronsted-Lowry acid and box the Bronsted-Lowry base. So now remember, the Bronsted-Lowry acid is the proton donor, and the Bronsted-Lowry base is the proton acceptor. And here, when we look at the reactions, only look on the left side of the reaction, the reactant side, to classify. Don't worry about the products right now. All right, so our first reaction, HCl plus H2O, goes to Cl minus and H3O plus. What's the acid? What's the base? Well, I want to see how the proton moves between these two molecules. So here it looks like this H is donated to H2O and leaves behind Cl minus and H3O plus. So here, HCl will be our acid, H2O will be our base. It accepted the proton. All right, question 2. H2SO4 plus H2O goes to HSO4 minus and H3O plus. So how does the proton move between these two molecules? Well, here I have 2 hydrogens next to my SO4. Here I just have 1 hydrogen. So it looks like a proton was donated from this molecule and accepted over here. So this is going to be my acid. This will be my base. All right, and last question here, NH3 plus H2O goes to NH4 plus OH minus. All right, so how does the proton move between these two substances? All right, well here it looks like actually the proton is leaving water and being donated to ammonia. So now I go from 3 hydrogens to 4. So in this case, water is the acid and ammonia is the base. So notice water can act as an acid or a base. So to summarize what we reviewed today and what we learned through this unit, you now know how to define an Arrhenius acid or base. You know how to define a Bronsted-Lowry acid or base. You can categorize a compound as an acid or a base given its formula. And you can identify a Bronsted-Lowry acid or base given the reaction. All right, so review your notes, rewatch some videos, and then take the acid-base quiz when you feel prepared. All right, if you have any questions, please reach out to your teacher in office hours, and that will finish up our unit on acids and bases.